First of all, I want to thank you for attending the conference, and of course, in the name of the department, Computer Science Department of the Tbilisi State University, I want to thank the organizers for being here and organizing such a conference. It's very important for us to have connections, tight connections with industry, and I'm sure that our talks at the coffee breaks and after it will be very fruitful for both sides. So thank you. Well, my name is Alexander Gamkrelidze, and once again I want to thank the organizers for inviting me as a keynote speaker. It's a pleasure for me to be here and give a talk about the applications of computational topologies to artificial intelligence. Well, I want to give you a brief overview of the subject without going deep into details or mentioning some details, just to give you a feeling how we can apply such a highly theoretical science to highly practical science, to computer science. But as it happens in science, we have our language, scientific language, is mathematical. This is our history. Our mind has developed the language of science. We translate our problems into mathematical language, try to solve it there, and then restore the answers and translate it back to our language. And now I want to give you some examples. How could we apply topological problems, the solutions of topological problems to computer science, and tell a little bit about the stuff we are doing here at our university, and discussing maybe how can we apply and improve the science of artificial intelligence with our results. Okay, first of all, I want to talk about why should we study topology for computer science, and give you some major changes that happened in the 20th century, mainly how we attack the problems, the mathematical problems, because the way we solve problems, or we look at mathematical problems in the 20th century and 21st century, it differs from the way we did it before, or science did it before. And then I want to give some examples of applications or some ideas how we can apply such stuff to artificial intelligence, and then talk about some technical aspects, because the modern ideas that are applied to artificial intelligence, they are based on so-called simplicial complexes. And the extension of the simplicial complexes are polytope complexes. And what is the categorical study of polytope complexes? And at last, I want to give some conclusions. What has been done and how can we go further with our work? Okay, now some words about topology. Topology is the science based on connectivity. We have the notion of neighborhood in topology. We don't have the notions of the distance. On contrary to geometry, where we have the notion of distance and 2 points are close to one another, topology deals with neighborhoods. There is nothing like distance in topology. And if we see here in the example, we have two balls. One is deflated, but the essence of this is that it's still a ball. Whether deflated or not, well, the right ball cannot bounce or cannot roll, but it's still a ball. It misses some physical aspects, but it's still the same as the inflated ball. So topology is the science that does not distinguish between those two subjects. But from geometrical point of view, they are different. So this is one of the good sides of topology. We can catch or we can grab the essence of the object, no matter how it looks. But on the other hand, from topological viewpoint, a cup is the same as the donut. Topology cannot distinguish between cups and donuts. This is the drawback. From topological viewpoint, those two things are the same, but in real life, they are quite different. So how can we apply such things to proceed in our science? Okay. Well, this is a nice picture, how topology. It's from Afra Zamorodyan. He's a famous researcher in the field of computational topology. And this is a famous picture of Salvador Dali. And he did it with topological objects. This is the same, a topological picture of Salvador Dali. Dali's picture, painting, and he called it persistence of homology. These are all the objects here are topologically the same. So black objects are the same, and the white objects are the same, and so on. But it's, well, this is also some stuff of topology. One of the main applications of topology can be restoring missing data. If we have some point clouds, so-called point clouds, so a collection of points in this case in three-dimensional or two-dimensional space, how can we restore the information or the points that are missed? This is a big problem nowadays in many fields of computer science and our real life. First of all is restoring some pictures, but also restoring missing data. We measure some data, some events, but we can't measure it continuously. We have to measure it point-wise. And how can we fill the gaps? This is one of the greatest problems. And topological methods help us to restore some data in point clouds, for example. Or we can extend the question and ask, how can we deal with big data? Big data is the same. The amount of data is so big that we cannot grab everything. So essentially, there is a same problem. How can we restore the information we are missing? So in principle, those two problems are identical, or not identical, but similar, very similar. One of the earliest applications of topology to computer science was the so-called Borsuk-Ulam theorem. It states that if we have a continuous mapping from an n-dimensional ball, n-dimensional sphere, into an n-dimensional space, there are two diametrically opposite points on the sphere that are mapped into one point. So, for example, in our real life, we have a ball we are living on. This is the Earth. And there are 2 points on the Earth that are diametrically opposite to one another, where the temperature and pressure are exactly the same. This is a very deep theorem, and it helps to solve many problems. Okay, this is an example of in 2 dimensions. If we squeeze the disk and lay it on the floor and flatten it, there will be always two opposite points that are on the same, that are mapped to the same point on the floor. Well, this problem, this theorem has helped to solve very important problems in discrete mathematics, into chromatic numbers of graphs. This is a so-called NP-complete problem, a very hard problem in general that asks to color the vertices of a given graph in different colors so that the neighbors have different colors. 2 vertices that are connected by an edge should have different colors. This is, and the number of colors used should be minimal. This is the famous chromatic number problem. And using the Borsuk-Ulam theorem, we can compute effectively the chromatic number of a special, very important subclass of graphs that is called the Kneser graphs. Okay, this is a famous result, and this is one of the rare situations where we can solve an NP-complete, a very hard problem for a large set of graphs, for a large class of graphs, of data. Another very important application is the theorem that we can divide a system into equivalent subsystems. And the division process is simple. So if we have a plane with different colors, colored points, but the set of the points with same color should be the same for each color. We have here 6 blue, 6 green, 6 yellow, and 6 red points. And those points can be divided into subsets. Each set contains exactly 1 member from each color. But the main thing is that we have convex hulls. That means we can do the separation easily. This is a very important result with many applications in data science and accordingly in many subfields of computer science. Okay, and this is all due to the so-called Borsuk-Ulam theorem. So this is a nice example how can we apply topology to computer science. And the main thing is that no non-topological solutions are known for such kind of problems. There are no combinatorial solutions for them. So we can say that studying topology gives us sometimes a deeper insight into the problems and problematics in general as studying with standardized methods. Well, now what about the major changes in the way we attack the problems in the 20th century? Since ancient times, there was a way to study an object if we have an object with a structure, maybe there is addition or multiplication or Lie brackets defined on the set. We have some mathematical object, some algebra on it. If we want to explore it, we have to experiment with the elements. We have to look inside and make some experiments. And as more experiments we have, the more insight we have about the system. Well, this maybe this is because we deal the problem in our real life this way. In physics, for example, we are making some experiments. We are experimenting with the objects. Or biology. The biologists are experimenting with their objects, and the physicists with their objects, and so on. And the mathematicians are also experimenting with the objects. But the main thing is that the way to attack a problem was to look deeper inside the object. Well, since the 20th century, there was made a very important observation that studying a system is the same as studying some homomorphisms. That means some functions or mappings from this object to a known object. But homomorphism means that the operation, we have the same similar operation here in the second object, and the results are also mapped into one another. So we have two elements in one system and two elements according elements in the other. If we make addition here and addition here, the results are also mappings, mapped in one another. This is called a homomorphism. But the main result was that studying all kinds of homomorphisms gives us the same deep insight into the system as experimenting with the objects themselves. So it means we have not to look inside and experiment with the objects, but we have to experiment or to know how the other system acts with our known system. And the other way round is also correct. If we study one system, if we study all the homomorphisms from a known system into the unknown system, this also gives us a deep insight into the unknown system. This is, well, here we have, if we have the possibility to investigate the homomorphisms from A to B or from B to A, this gives us the same result or the same insight into the object A as if we experimented with the objects. And this is called to build a duality, a dual system. We investigate a dual system, and this gives us a deep insight into the original system. This is the way problems are tackled in the 20th century. And this is pretty much the same as if we want to observe some far galaxies or far objects. We have no opportunity, no way to look inside and experiment with the objects. We have to know how this faraway galaxy acts to our known system, in this case, our system that measures some influences from the faraway galaxies. And this gives us a deeper insight into the far galaxies. And if we had the possibility to know all the influences, we would have complete information about the galaxies. This is the same how our way to attack problems, mathematical or algebraic problems, changed in the 20th century. Well, the main thing was to compute so-called homology classes. And this is to count how many holes an object has. Here we have a donut, it has one hole, and we have two circles that define those holes, only two circles. We can have two circles, two different circles on this surface, and we have an object with three holes on the right-hand side. And here we have 1, 2, 3, 4, 5, 6, 7. 7 generators, so to say. So computing the generators of homology classes gives us a deep insight into the structure of the object. And if we have some information data, for example, measured data, and we want to determine the pattern of it, we can deal it the way that imagine that this data lies on the surface of some object, and how should the surface be? How should the surface look like to embed the data on it? And the topology of the surface will give us the patterns of different data, different patterns for different data. Well, one of the first algorithms that was given to compute the generators of homology groups was published in 1953 in Duality. It was computation of the Chern cycles of algebraic manifolds. And well, this is basically this is a formula, but it gives us the first algorithm how to compute the generators and how to compute the number of holes and the structure, topological structure of some objects. And since that, many sophisticated results were published. The main thing comes from the basic idea of Marston Morse, who developed the Morse theory, how to define the structure of an object if we investigate the functions, differentiable functions on it. This was the theory, Morse theory, and his main idea was to scan an object. We have to embed an object into a space and then look at the levels, or some levels of the space, cutting the object and looking at the cut. What do we have? What kind of structure do we have on each cut? Maybe I have here. Okay. We have on the left-hand side a picture. We have cutted the objects. We have touched the object in 2 points. And this gives us the picture that 2 points are touched, and the touching space is increasing. On the other picture, we see that 2 spaces are merging, but another here in the middle, in the first picture in the middle, a new space was born. And this space has merged with the space around. And in the third picture, we see that some spaces are vanishing. Some holes are vanishing, building new holes. And at the end, we have all holes, only one hole left. And at some moment, this hole will be glued, and we will have no holes at all. So examining in the homologies in time gives us a deep insight into the object, how the topology of the object is. And this is the persistent idea of persistent homology, is the basic idea now to apply topology in different fields of computer science. This is maybe nowadays one of the most popular problems, computing persistent homology for objects. It was first given in a talk by Edelsbrunner, an Austrian scientist, in 2008 at the European Congress of Mathematicians. It has a wide range of applications because, for example, if we look at the same picture with noise, we can build the so-called diagrams, barcodes, for different topological objects, for different homologies, and examine what kind of homology leaves the most time. Because the homologies, the changes that are induced by a noise, they are not long-living. They die or vanish in a short time. So we can discard all the things that are producing short-time homology changes. And this can be observed as a filter or filtration. Or we can examine many other structures by examining what kind of homology is lasting for long and what time for a short time of period. Well, and what kind of applications can we have with it? It's, of course, denoising. Denoising, I mentioned already. It's an expert analysis. For example, we have estimations of different experts, but there should be some divergences. But if we have many experts in a field, the divergences will be like a noise. So we can examine the data in the sense of persistent homology and look at the data that is short-living. And this can be observed as the divergence from the normality of the expert analysis. We can analyze in face recognition. This is a straightforward application, face recognition, recognizing similarities in some objects. We can apply it to neural network or network analysis for the same reason. What is the short-living result? For example, if we teach some neural network, and we can look at the homologies or persistent homologies on it. The short-living homologies are the errors or divergences also. So it's all about analyzing the data, the noise or divergences in the data, also in big data and missing data. What data can be missed in the neighborhood of some data area? It can be only that is similar to the neighborhood, and so on. There are many scientific investigations and many scientific papers in this field, so it's not a problem to find very interesting results on the internet. Okay, the main thing to study homologies are the so-called simplicial complexes. If we have a complex object, we have to triangulate it, to divide it in small triangles, because acting with triangles is much more easier. So triangles are so-called simplices. Simplex is a triangle. And glued triangles build a complex. It's a simplicial complex. Well, a simplex can be defined as follows. Zero-dimensional is a point. A line is one-dimensional. Triangle is two-dimensional. A pyramid is three-dimensional, and so on. We take an n-1 dimensional simplex and add an additional point in additional dimension and connect this point to the points in the n-dimensional simplex to get a larger simplex. This is how a simplex is built. On the contrary, we have an n-dimensional polytope. A polytope is an extension of simplex. It's a geometric figure that we obtain by cutting an n-dimensional space by n-1 dimensional spaces, hyperplanes. For example, here we have 1, 2, 3, 4, 5, 6 cuts, and we get such a geometric object. And the polytopes, they carry information, geometric information, in contrary to the simplices that are purely combinatorial. There is no geometry in it. But polytopes, they carry information, both combinatorial and geometric information in it. Well, we have some complexes, polytopal complexes and simplicial complexes. That means we glue objects together, but the gluing should be on the same dimensional faces, sides. You can glue, for example, a point of one subject to the plane of the other one. It's point to point, vertex to vertex, edge to edge, and plane to plane. The same with the polytopal complexes. And polytopal complexes carry the complete information of simplicial complexes, and the main tendency nowadays is that we take simplicial complexes, we embed the simplicial complexes on the surface of the object we want to investigate, and then count the homologies on it. But another advantage of polytopal complexes is that we have also non-Euclidean polytopal complexes. That means that we can not embed those things into Euclidean space, into our world. It should be much more complex space, taken a complex space to embed them. And if we have data, some data we want to examine, and the pattern of data is so complex that we have to describe it in non-Euclidean spaces, then the simplicial complexes will not suffice to investigate the patterns of the data. There should be applied polytopal complexes applied. So this is another motivation of developing a theory about polytopal complexes. Here we have structure of our polytopal complexes, and on the other hand, the so-called Kozlov complexes. This is a generalization of the well-known Lovász complexes based on the Lovász lemma that says, it's a very important Lovász lemma, says that if we have a space of information and we have some bad information, bad news, we always have a way to avoid this bad information, to have a strategy to move in the space, always to avoid with certainty, with 100% certainty, to avoid bad points. This is a very important theorem, and based on it, Lovász has developed his complexes. Kozlov has extended this, and the set of polytopal complexes implies the set of simplicial complexes that is also included in Kozlov complexes. This is the point where those two constructions meet. So it's another motivation. Polytopal complexes are not just an artificial thing, but it fits into the known theories, already known theories. So we have the same structure as I showed in the motivation, in the changes of the way we attack the problems. If we study homologies from A to B, and A and B are polytopal complexes, and those are the affine mappings. That means it's all linear mappings. This set of linear mappings, it builds a polytopal complex itself. So studying this polytopal complex would give us a deep insight into the structures of A and B. Or we can map A to itself. And the theory, the first steps in the theory of polytopal complexes and the proof that this structure is a polytopal complexes was given in 2016 in a paper with my co-authors and friends, Malchas Bakuradze and Joseph Gubeladze. Okay, now to the conclusions. We have seen that topology, or it's well known that topology plays an important role in computer science in general and in artificial intelligence in particular. And the actual trend is to describe objects with simplicial complexes and apply persistent homology to investigate their shapes. And the problem is that some objects cannot be described effectively by simplicial complexes. Now our question is, can we describe them with polytopal complexes and apply the same ideas of persistent homology effectively to the polytopal complexes to study the pattern of complex data that does not fit into Euclidean space? That's all. Thank you for your attention and patience.